You are watching one of a series of videos giving an introduction to OrcaFlex. The first 4 of these videos, which we've called the fundamentals, are those that we would regard as prerequisites for looking at any of the other subsequent topics. If you are already familiar with these fundamentals, you may want to pick and choose the subsequent videos you watch based on your area of interest. If you're a complete beginner with OrcaFlex, I would strongly encourage you to watch the full series in order, as this will give you a good basic overview of the program, how to navigate it, and where to access and input data. It goes without saying that the quality of any OrcaFlex analysis is only as good as the quality of the input data, and that, of course, relies on the skill and experience of you, the user. These videos will help you to learn how to use OrcaFlex as one of your analysis tools, and I do hope that you find them educational and maybe even a little bit enjoyable too. In this video, we will take some time to learn about the constraint object and how it can be used in an OrcaFlex model. Constraints do not have any physical properties themselves, but are intended to provide connections between other objects. They have 2 frames of reference, with their typical use case having one frame of reference connected to a parent object and the other connected to one or more child objects. There are some special cases where it is possible, via the use of a double-sided option, to have both frames of reference connected to parent objects. An example of this is for floating solar arrays, where adjacent panels can be connected via double-sided constraints. We'll briefly see an example of this later. The great benefit of constraints is that they can allow degrees of freedom to be selectively enabled or disabled between parent and child objects, or to have imposed motion. This makes them ideal for modelling things like hinges and slide rails, or for imposing motion in particular degrees of freedom to simulate such things as crane motions and reeling operations. I will create a simple model first of all to demonstrate their use. For this, I will include a vessel, a buoy, and a constraint, all in arbitrary positions. We'll connect these in series, with the buoy connected to the constraint and the constraint connected to the vessel. The order of relationships with constraints is very important, as it is the child objects whose behaviour is influenced by the constraint settings, be it calculated degrees of freedom or imposed motion. With this model, the buoy is child to the constraint, which is then child to the vessel, the parent object. If I drag the vessel around the screen, both the other objects follow, since the vessel is the parent. If I move the constraint, only the buoy moves with it, since the constraint is parent to the buoy. If I run this analysis, the resultant motion is through the use of displacement RAOs in the default vessel. The constraint and buoy are both rigidly connected to the vessel. Let's reset the model and look at the constraint data form. This is the first type of constraint, which has calculated degrees of freedom. On the degrees of freedom page, we can choose to enable one or more degrees of freedom by ticking the adjacent boxes. This will then allow the child object, the buoy, to move independently of the parent object, the vessel, in whichever degrees of freedom are enabled. For example, with rotation around the y-axis, RY, enabled, watch the resultant behaviour. As the vessel moves in response to the passing waves, the buoy is allowed to rotate around the y-axis of the constraint. Rotating the view shows that the arrow adjacent to the y-axis label is green, indicating that this degree of freedom is enabled. As the buoy rotates, we also see a second set of axes rotating with it. Opening the constraint data form and looking at the drawing page, we see the 2 frames of reference. The in-frame axes are the solid axes connected to the parent object, in this case the vessel. The out-frame axes are the dotted line axes connected to the child object, the buoy. Now let's reset the model and change to a translational degree of freedom. In X for example. Now the X label in the 3D view is green, indicating that this is the only enabled degree of freedom. The resultant response now is that the boy is free to slide along an imaginary rail on the X-axis of the constraint. And you can see the out frame moving with it, while the in frame remains rigidly connected to the vessel. At present, this motion is totally unrestricted. We can optionally apply stiffness and damping to resist the displacement and velocity of the out frame relative to the in frame. This can be linear, as we can demonstrate now by adding a translational stiffness of, say, 10 kilonewtons per meter. And this results in a significantly reduced displacement. We can also apply nonlinear values using a variable data item. An example of this is to model physical stops at the ends of a sliding rail or the rotational stops on a Stinger roller box. Let's introduce a nonlinear translational stiffness now to this example. In this case, I would like to allow unrestricted movement along a certain distance before ramping up the resistive force to simulate a physical stop. After returning to zero translational stiffness and rerunning the simulation, a time history of constraint X shows us a displacement of around 38 meters at the end of the simulation. I would like to limit this to plus or minus 10 meters. If I reset the model and select the down arrow adjacent to the translational stiffness value, this lets me access the variable data form, where I can create a new data source. I'll need a minimum of 4 rows of data here. At either extremity, I need to set the point at which the force is ramped up from 0 to a force that is high enough to resist the inertia of the outframe and its connected child objects. The middle 2 rows set my desired maximum displacements of plus 10 and minus 10. And then the outer 2 rows set the point at which the value is ramped up. Obviously, the closer this value is to the maximum displacement, the steeper the ramp. For a hard physical stop, this would need to be a very short distance. I'll use a ramp distance of 0.1 meter, up to a maximum force of 10,000 kilonewtons in both directions. We can check the profile graphically and also optionally apply hysteresis to the stiffness if appropriate. Selecting the new variable data item and then rerunning the simulation, the same time history as before now shows the displacement is limited to plus and minus 10 meters as required. So far we have only looked at the calculated constraint type, with the positions of the objects connected to the outframe calculated based on the loads acting on them. We can also choose to impose a motion on the outframe of the constraint, much like a prescribed primary motion on a vessel object. When the model is reset, and we select Imposed Motion as the constraint type, the colours of the axes change to indicate this. The motion of the outframe is now imposed and can either be specified as a set of time history data or externally calculated using an external function. The time history data can be specified in an external text file, which is useful if multiple models are referencing the same data. Alternatively, it can be an internal data source, specified directly on the constraint data form, which is what we will do now. The time history page can be filled out as required. Note that it should cover the time periods defined in the stages on the analysis page of the general data form, otherwise an error will be reported. The default times in OrcaFlex go from minus 8 seconds to plus 16 seconds. If I try to use an imposed motion with data from 0 to, say, 10 seconds, I will see an error, which tells me the problem and also provides a helpful link to the relevant part of the documentation. Going back to the data form and defining an appropriate set of data, I want the buoy to start moving forward by 50 meters relative to the vessel from time 0. The time history preview shows the motion I can expect, and I can see an unexpected negative displacement at the start of the curve. This is because cubic spline interpolation is used by default, as it gives continuity of velocity and acceleration. We could provide more data points to avoid the negative displacement, or we can select linear interpolation on the time history source page. For this simple example, this will give the desired behavior. Running the simulation and viewing the replay, as well as the same constraint X time history, this shows the displacement of the buoy relative to the vessel. We could elaborate on this further by adding an intermediate time. We are not limited by stages in the creation of a time history. I will add an intermediate time at 8 seconds and specify 50 meters displacement in X from 8 seconds onwards. Also, from 8 to 16 seconds, I will rotate the buoy around the y-axis to a value of 180 degrees by specifying 180 in the final row for Ry. Having run the simulation, we now see the buoy is moved forward and then rotated around the constraint axes, with the relevant constraint results also shown on screen. This kind of imposed motion can be used to model such things as cranes, where imposed motion constraints can be chained together to simulate the various luff and slew rotations. This example shows a crane performing an overboarding operation with a series of imposed motion constraints being used for the crane motion. Note that the visual appearance of the crane uses a number of drawing shapes, but the actual motion is all driven by the underlying constraints, which we can see more clearly if we hide the drawing shapes. It is also interesting to note that the vessel in the model is calculated, meaning its motion is affected by the loads acting on it. The stern view shows how the vessel roll increases as the payload moves overboard. I should note that we don't recommend performing an overboarding operation with this much motion. We've exaggerated the response of the system as part of the demonstration of the constraint object. We gave a presentation on constraints as part of our 2016 user group meetings, including a number of examples like the crane. And the material from this presentation can be downloaded from the UGM material page of our website, as shown on the screen. To practice using constraints, we will look at a worked example now. We will build a simple wave energy converter which will use constraints to connect some rafts together. The first exercise is to edit the data for the environment, which includes setting the water depth, waves and current as shown in the table. So we'll set a 20 meter water depth, a 1 meter 5-second wave, and a 1 meter per second current. All other environment properties will be left at the default settings. Having set the environment data, we will build the first raft, which comprises a 6D buoy plus 2 lines which will act as buoyancy tanks. The data used to build the raft is shown on the screen. Let's insert a 6D buoy to represent the raft and position it at the global origin of 0, 0, 0. On the properties page, we will change the volume to 20 cubic meters and the height to 1 meter. The only other change to the buoy data is that of the drawing data. As mentioned in the buoy video, this data doesn't influence its hydrodynamics, but would have an effect if contact with the seabed was to be modelled. We will change the drawing data for visualization purposes using the vertex information in this table. I have this information in an Excel table, so it's very easy for me to go and copy and paste it. Next, we will create the first of the buoyancy tanks using the data in this table. Note that the line has midline connections defined. This will connect every node to the buoy, effectively making the buoy and the line a completely rigid pair. We have to place a new line into the model to be able to access the line type data form. The name is buoyancy, and the only other data to change from default line type settings are the outer and inner diameters of 2 meters and 0. The mass per unit length of 0.001 and an axial drag coefficient of 0.1. Now we can move on to the data in the line data form. It is called tank A1 and has a length of 10 meters and a segment length of 2 meters. End A is connected to the 6D buoy at a position of -5, 2, and -0.5, and end B at a position of 5, 2, and -0.5. Both ends need a declination of 90 degrees and infinity end connection stiffness. As mentioned, the mid-nodes in the line are connected to the buoy by way of 4 midline connections. At arc lengths of 2, 4, 6, and 8. The connections should be to the 6D buoy with X positions of -3, -1, 1, and 3. All Y positions are 2 meters, and all Z positions should be -0.5. And all should have declinations of 90 degrees. This connects the first buoyancy tank to the raft. The line representing the second tank is a duplicate of the first with a different position. So we can copy and paste the line we have just created, adjusting the positions as in the new table. Just before I do that, I will also rename my buoy, and I'll call that carriage 1. The second line is only different in its position in the y-axis. So we need to change the y positions for both ends from 2 to -2. Likewise for the midline connections. These two buoyancy lines should now be correctly positioned on either side of the principal axis of the system. The next part of the model we need to build is the first mooring line. This will be created as a chain using the line type wizard with data in the table. We need to create a line type using the wizard, so we'll go to the line type data form. Importantly, we can't just open the wizard now, as that will modify the existing line type. We need to first add a new line type called chain. Make sure this is selected and then open the wizard. And this just needs the chain option selecting, and on the next page the bar diameter adjusting to 0.025. Now we can add a new line called mooring 1 with end A connected to carriage 1 at a position of 5, 5, -0.5, with end B anchored at 35, 5, and with a height above seabed of 0. On the structure page, its length should be 40 meters, segment length 1 meter, and make sure the chain line type has been selected from the drop-down list. Note that as we've just changed the line type, we need to return to the anchored end of the line and reset the height above seabed. This is because the height above seabed takes into account the diameter of the line selected. Having created the first mooring, we can easily create the second, again by copying and pasting the first. The only subsequent changes needed for the new line are the Y positions for both ends, with end A being changed to -5 and end B to -5, and everything else is already set. Even though we only have one of the 3 rafts, we should now be able to run statics. We can even run dynamics and look at the response of a single floating raft. However, power generation from a wave energy converter like this comes from the relative rotation between rafts, so we need at least one more. To create a rotation or a hinge between rafts, we're going to need a constraint, and this will be built with the data in this table. So the constraint will be called connection 1. It will be connected to carriage 1 at a position of -5.5, 0, -0.5, and all other properties will be default. Now that we have one raft set up, I'm going to suggest grouping the objects in the model browser to make the job of creating additional rafts more straightforward. The first thing I will do is create a group called moorings. And you've guessed it, I'm going to put the moorings into this group. Next, I will create a group called raft 1, and in this I will put all the other objects. Note that this includes the constraint because this will be needed for connection to subsequently created raft groups. Now I will copy raft group 1 and paste it into the top level folder. Note that with careful naming of the original objects, I have sensible names for all of the objects in the second group, including the group name. Now I just need to reposition it. Instead of being free, the second boy, carriage 2, needs to be connected as a child to the first constraint, connection 1. Once this new connection is made, the initial x position of the boy needs to be changed from 5.5 to -5.5 meters. This gives us 2 rafts, and we could easily repeat the process by adding a third raft. Copying the raft 2 group and pasting it again into the top level folder. Again, we need to open the new boy data form, carriage 3, and adjust the connection from the first constraint, connection 1, to the second, connection 2. Once again, the initial x position needs to change to -5.5 meters, placing the boy 5.5 meters behind the constraint. Dynamics can be run now, but at this stage, the 3 rafts are acting as one rigid body. The final step is to enable the appropriate rotational degree of freedom on each constraint, in this case RY. Connection 3 doesn't yet have any child objects connected to it, so it doesn't need to be changed. If there were to be further rafts, we could leave this constraint here, otherwise it could be deleted. So we'll set connection 1 to have RY free, and the same for connection 2. And we'll rerun dynamics and take another look. So we can see in dynamics the replay shows we now have relative rotations between the rafts, allowing us to capture some of that wave energy. Before we finish the constraints discussion, I want to briefly introduce two more advanced settings. The first of this is the curvilinear model type. This allows the motion of the outframe to be restricted to arbitrary curves and surfaces, as well as the dynamic release of the outframe based on user-specified criteria. The curves and surfaces are defined as a mathematical mapping using Python and input on the coordinates page of the constraint data form. We can define one or more free coordinates if required, and then a mapping which defines the constraint in Cartesian coordinates as functions of the free coordinates. One free coordinate will result in a line being generated along which the constraint will be restricted, and two free coordinates will result in a surface being defined. It is also possible to impose motion with a curvilinear constraint by setting 0 free coordinates and then defining a mapping as a function of time. In this case, you do not need to define any free coordinates because the position of the constraint outframe relative to its inframe is completely prescribed. We'll create a parabolic curve as a simple example. First, with a constraint inserted into a new model and the curvilinear model type selected, then we'll add one free coordinate, A, and a mapping which includes x equals 5a and z equals a squared. Note that as this is a Python mapping, we need to use the appropriate syntax for these mathematical expressions. A curve is now drawn, along which the constraint outframe will be restricted. Let's now insert a buoy and connect it to the constraint origin. Running this analysis results in not much of interest happening, but let's make a couple of changes. First, we'll turn off whole system statics on the general data form. Then we'll open the constraint data form and set an initial position for free coordinate A as 10. This places the buoy at the top of the curve, and when we run dynamics and look at a replay, we see the buoy falling down the curve. This example shows how a dynamic release can be created with a force being defined as the release condition. In this case, we require the line to release when a certain force is reached at the connection between the line and the vessel. To do this, a constraint is placed as a connection between the line and the vessel. The line is child to the constraint, and the constraint is child to the vessel. The constraint data form has no free coordinates defined, so the inframe and outframe are rigidly connected. However, we have specified an outframe release condition when the force exceeds 2,500 kilonewtons. As the vessel is driven back, the mooring tension increases until the release force is reached, at which point the constraint outframe is released and the line falls away to the seabed. We can confirm this by looking at a time history result for outframe connection force. A further example shows how a dynamic release can be used in conjunction with a free coordinate. The requirement is to allow the buoy to slide along a rail and then fall off the stern of the vessel. The buoy is child to the constraint, which is child to the vessel. The constraint has a single degree of freedom defined, x, which allows the buoy to slide along the x-axis without restriction. This can be done with a standard Cartesian constraint, but the curvilinear model type allows us to also specify a release condition. In this case, the constraint outframe, and therefore the buoy connected to it, will be released when the displacement in x goes beyond -10 meters. At the start, the degree of freedom labels are all red, apart from x, since it's free. After the displacement exceeds -10 meters, the remaining fixed constraint labels change from red to green, and the buoy falls into the sea. There are a variety of examples of curvilinear constraints in the documentation, so please make use of this if you would like to know more. The final advanced constraint option I would like to show you is one that I mentioned earlier, double-sided constraints. Double-sided constraints allow their in-frame to be connected to one object and their out-frame to another. This is often beneficial in avoiding circular connection dependencies that can sometimes occur in complex models such as floating solar arrays, commonly known as floating photovoltaic or FPV arrays. These types of system with multiple interconnected panels are often difficult to model using the standard single-sided constraint as a connection between panels. Here we have a simple example of an FPV array with 4 panels connected via double-sided constraints. The panels themselves are free, and each constraint has in-frame connected to one panel and out-frame connected to another panel. Thus, the constraints are child to 2 parent panels. Along one axis, the constraints have a single rotational degree of freedom, representing a hinge. Along the other axis, the constraints have 6 degrees of freedom, but have a high translational stiffness, so can therefore only rotate, being free to do so in all 3 rotational degrees of freedom. This particular set of constraints represents a flexible skirt arrangement, common in arrays like this. Again, we can use some results to confirm the desired motions. In this case, the rotational time histories for 2 of the constraints. That completes our discussion on the constraint object. We'll move on in the next video to look at environment settings.